Hello, everyone. We're working through statistical methods for rates and proportions, Chapter 8, Randomized Control Studies, Section 8.3, Factors Affecting Power in a Randomized Control Trial. We're first going to talk about Section 8, subsection 8.3.1, the intent to treat principle. So why did they even have to come up with this principle? Overall, in a study, there's always dropout or crossovers that may happen with patients, right? Patients might need to be removed from the study for some health reason before the end of the trial. This removal may be temporary or permanent. People move away. People might pass away during their study. Or sometimes the patients just may not adhere to the treatment and might do a different treatment than was assigned to them, right? So we call this a crossover. A patient that's assigned to one treatment arm, in fact, receives all or part of the intervention from the other treatment arm. Okay, so what is intent to treat principle overall? Essentially, the goal of the intent to treat principle is that you're going to preserve the type 1 error rate in the presence of crossover of the patients. So once you randomize a patient, no matter why they switch treatments or drop out or do something else, you're going to analyze those patients, okay? Patients are analyzed as members of the groups they were originally assigned. So even if they switch treatments from treatment A to treatment B, they're going to still be assigned as if they received treatment A. For clinical trials, almost all clinical trials for primary analysis use this intent to treat principle. So it's really important to understand that you'd be using this if you were working as a biostatistician. All right. If you have non-negligible crossover or non-adherence, you do need to be careful to interpret this just because if people are crossing over, you are looking at an effect of crossover. So you just need to be aware of that. All right. For subsection 8.3.2, we're going to talk about non-inferiority and equivalence trials. Okay, so a non-inferiority trial is when we are saying, is a new treatment not substantially worse than a standard treatment? And not substantially worse, we call this the limit of indifference. All right. Whereas for an equivalence trial, we're saying, is the new treatment neither substantially worse nor substantially better than a standard treatment? And in the range of not substantially worse to not substantially better, we call this the zone of indifference. Okay, you might be asking why we would want to look at this. Well, let's suppose a standard treatment is very expensive or has a lot of side effects. We may want to consider other treatments that are more cost effective or they have less side effects. So overall, we don't need the new treatment to perform better than the standard treatment in this case. We just want to make sure that you're not performing substantially worse or substantially different than the standard treatment. Okay, so we're going to set our delta, something greater than 0, to be the limit of indifference, right? So that is as far down as you'll go where you're saying that the treatment's not substantially worse than the standard. All right, P0 is the success rate for the standard treatment, and P1 is the success rate for the new treatment. Okay, so first we're going to consider the hypothesis that goes along with the non-inferiority trial. All right, so we're testing HO is P1 less than or equal to the standard treatment minus some delta, right? Versus HA that treatment 1 is greater than that limit of indifference, right? From our standard treatment to the limit of indifference. Okay, so we're gonna set our alpha level to be 0.05 and our beta to be 0.20. Remember, our power is 1 minus beta by definition. We can get our Z alpha to be essentially you put in this alpha value and you can actually get the value of z associated with that. We're using that Q norm function in R. We designate lower tail equals false. That's guaranteeing us to get the positive z value associated with 0.05 above it. So if we look at that, we get 1.645, just what we expected. All right, we're going to set delta to be 0.05. All right, so what we're going to do is we're going to consider calculating power. And if you look in the text, we're looking at equation 8.17 and 8.18. All right, so I'm going to create a function that is going to figure out and solve for P0 hat. So if you look at equation 8.18, there's two terms, right? They have to be equal to 0 when you add them together to be able to figure out P0 hat, okay, which is the maximum likelihood estimate of the standard treatment success rate, subject to the constraint that the difference between the success rate is at the limit of indifference. Okay, so what we're doing here is we're specifying term 1 of 8.18, okay? And then we're specifying term 2 given in 8.18. And then that equation says take term 1 plus term 2, right? And when it equals 0, that's going to give us our estimate of P0 hat. All right, so this epsilon that I'm setting is just to say I want to get values above or below 0. So I'm going to look at the absolute value of this summation. And I'm going to say, when am I close to 0? Because essentially, I don't want to look at all the possible values of P0 hat. So if we look at this, we run our function. And if we have equal sample sizes, let's suppose N0 is 50 and N1 is 50, and we consider all these different values of P0 hat. So remember, P0 hat is some number between 0 and 1, and I'm going to just step by 0.01 here. And when I do this, okay, so we are going to consider a lot of different P0 hats somewhere between 0 and 1. And right now I'm just doing a step of 0.01. So we're going to consider values of P0 hat that are just 0.01 apart each time. We're going to set each of our sample sizes to be equal. And we're going to initialize P0 and P1 to be equal because under the null hypothesis, they are a value that are very close together, something smaller than delta apart. Okay, so when I do this, I'm looking for a value that's very close to 0. So we know that the value is somewhere between 0.77 and 0.78. And what I should do is I should probably have these step sizes rather than being 0.01 apart. We want the step sizes to be more fine grained. So I'm going to do 0.0001 apart. Okay, so I'm going to look at those same values at a sample size of 50, but now I'm going to have a finer grained step size. And when I do this, I look for the value that's very close to 0, right? That's somewhere between 0.7733 and 0.7734. All right, so essentially we're looking at the value of P0 hat that satisfies equation 8.18. Now, what's interesting is if we look at this, regardless of the sample size that we get, notice that we're getting the same value of P0 hat. So it's really not dependent on the sample size changing. What's important is these initial values of P0 and P1 to be able to calculate this, and the fact that the sample sizes are equivalent. Because in all these different cases of these sample sizes, I'm getting the same value of P0 hat. That's a good thing. Okay, so for equation 8.17, what we're going to do is that equation actually depends on the value of P0 hat. So we're going to use our value of P0 hat And if we wanted to, then we could use the test statistic given in 8.17 to carry out the hypothesis test. But essentially, first, you have to solve equation 8.18 to figure out what P0 hat is, and then you could do the test based on 8.17. But the main point of this chapter is actually to talk about the power of the test. So we can use equation 8.19 to look at the power. Okay, so in this case, we're going to have to use P star 0, and we're going to use that value that we just found from P0 hat of that 0.7733. We need our sample sizes. We need an alpha level. We need our population proportion P0 and P1, and we need our delta. Okay, so we can read in our function for get power 8.19. Okay, and here we go. So we're going to say, what is the power when P star 0 is 0.7733? We have a sample size of 50 for each group, an alpha level of 0.05, and then P0 is 0.75 and P1 is 0.75. What's the value of the power? So we get a very low value for power. That is 0.0969. Obviously not a big enough sample size. So we say, okay, well, what if we jump that up to 500 people per treatment, and we get a power of 0.54, not quite at 80% that we'd like to see. Okay, what about 968? We throw that in. Now we're getting to the right values up at 80%. And then we could look at 1025 in each of those. That gets us to 82% power. All right, we're going to come back to this because obviously you don't want to just put in random numbers for your sample sizes. You're going to want to be able to calculate the power just straight out and know how big of a sample size do I need to achieve 80% power. We'll get to that, don't worry. All right, so in the equation 8.20, this says if you have equal sample sizes, then equation 8.19 can reduce, and it reduces in this way. So essentially, we're plugging in equation 8.20, and what we're doing is we're going to get the same values of power. Okay, so essentially 8.19 could have worked whether or not the sample sizes were equal or not, but 8.20 is in the specific scenario when those sample sizes are equal. Okay, so once again, we could say, okay, what's the sample size at 50, when the sample size is 50, what is the power in this situation? Or we could look at this for 968. We get those same values of power, which we should, given the scenario that we have. All right. The textbook goes on to say, well, what if we did a conventional test rather than an inferiority trial, right? And then what would the power be in this situation where it's the same exact setup? How many patients would I need in a conventional hypothesis test versus how many patients do I need in a non-inferiority trial? Okay, so now we're looking at equation 8.21 in the textbook. And we've shown that we could create a function to calculate the power, right? And those equations are given in the text, right? And furthermore, we can look at these values, right? So in a conventional test, if I had 50 patients per treatment, what would my power be? Still super low if I had 50 patients. Okay, if I had 500 patients, 0.52. And remember, we got to 80% power when we got to 968 patients, but here we don't reach 80% power in a conventional test yet. And then we check 1025 and we finally get to 80% power, whereas before we were at like 82% power, I believe. Yeah, it's right there in our history. Right here, 82% power. So what does this say? Essentially, if you're going to carry out a conventional hypothesis test, you're going to need more patients to get to significance rather than a non-inferiority trial. And pretty much this is because in the conventional test, we're testing whether or not, right, you are larger or if you are different than the hypothesized proportion. Whereas in a non-inferiority trial, you're just saying you're not worse. So it's not as powerful of a statement to say you're not worse, which means that you're not going to need as many patients to get to that significance. Okay, so as promised, I said that we would look at a scenario where we were able to just calculate the power for lots of different values of our sample size. And what we're going to do is we're going to create a plot that looks at the power calculated under 8.20 and the power calculated under 8.21. Now, just as a reminder, the power calculated under 8.20 is for the non-inferiority trial, whereas the power calculated in 8.21, that's your conventional hypothesis test. So in order to do this, we can make all those calculations and we can get a plot of the power, and we're going to put a horizontal line at 80%. And the black line is going to be for the non-inferiority trial, and the blue line is going to be for the conventional hypothesis test. So when we run this, we notice that in the beginning for small samples, our power is about equivalent. But then as we get to bigger sample sizes, this black line for the same number of patients ends up having slightly higher power than the blue line. And this carries through all the way. So essentially, if we say 80% power, when the non-inferiority trial hits that power, the conventional hypothesis test is not yet there. So it takes more patients under the conventional trial to hit the same value of power as a non-inferiority trial. So it really depends on what your goals are. Do you need a conventional hypothesis test, or do you need to just say that the new treatment is no worse than the old treatment? So there is a difference in that hypothesis question, right? In the non-inferiority trial, we're saying, is the new treatment not substantially worse than the other? Whereas in the conventional trial, we're saying, is the new treatment better than the standard treatment? So they're slightly different questions. They require a different number of patients depending on what you want to say. So it's important to recognize those differences and be able to calculate power in each of those scenarios so that you know how many patients that you need to sample in order to determine your results. All right, thank you for listening, and I'll see you in the next video.